Good morning. My name is Shankar Mandal, and today I will be speaking about secure hash algorithm 256, which is a highly popular cryptographic hash function used in the society today. In this presentation, I will cover the following topics: the use of SHA-256 in cryptocurrency, its brief history, overview of how it works, its properties, algorithm, and then finally its other applications. So what exactly is a cryptographic hash function? To provide a background for it, I will first talk about Bitcoin, which is actually recently gaining more popularity. So Bitcoin is a decentralized digital currency. It is a type of money that is completely virtual and is regarded as decentralized because it can be bought, sold, or exchanged without an intermediary such as a government or a banking institution. This is why it is said to operate under a peer-to-peer system where individuals can make transactions directly with each other. However, without the essential governing authority, how can these individuals prove their transactions? How can we be sure that they actually paid for something? Or better yet, how can we even know that they had the money at all? This problem is called the double spending problem. It is the risk of digital currency being spent more than once, being completely virtual. This form of money makes it possible for people, especially those with the knowledge and computing power, to simply produce copies of the digital money and spend it for multiple times. This is avoidable with traditional physical currencies because this type of money cannot be replicated. Furthermore, people have a more evident way of proving its authenticity and its past ownership. However, this is not the case with regards to virtual currencies. Fortunately, the creator of Bitcoin, Satoshi Nakamoto, devised a solution in October 2008 called the proof of work. So, what is proof of work and how does it work? Proof of work is a consensus algorithm that is used by Bitcoin and other cryptocurrencies to verify transactions. In order to explain how this is applied, I first need to introduce the concept of a blockchain. So, Bitcoin is built on what we call the blockchain technology, which is a public ledger that contains the history of every Bitcoin transaction that ever occurred. It is composed of a series of blocks, each containing the following: data about previous transactions, cryptographic hash of the block that it extends, or the hash of the previous transaction, and the timestamp showing the time of the block's creation. So, how is the blockchain related to the proof of work? Before a block can be added to the blockchain, it must first have a valid proof of work, which can only be achieved by solving cryptographic problems. This activity is called Bitcoin mining, and the people who perform these are called miners. Any network participant can be a miner, and the miner who generates a valid proof of work first will be given a free Bitcoin as a reward and compensation for the computing power that he or she spent. However, it must be noted that only those with very strong computing power are likely to solve these highly complex cryptographic problems, especially with the conception of large Bitcoin mining farms with expensive and fast computing resources. Mining has become more and more challenging. But what are these cryptographic problems anyway? In order to find a valid block, a miner is tasked to generate a hash that satisfies the specific condition provided by the network protocol. He or she must hash three things: hash of the previous block, the data of the set of transactions that will be added to the blockchain, and announce, which is short for number only used once. That's nonce is repeatedly incremented the block until its value given the required number of 0 bits that are specified by the network protocol, also known as the target. The particular hash function used by the Bitcoin is known as SHA-256. SHA or SHA stands for Secure Hash Algorithm, and the 256 simply means that it outputs the 256-bit long string. SHA-256 is actually just one type under the SHA family of hash functions, which was first introduced in 1993 by the National Security Agency with SHA-0. After 2 years, the National Institute of Standards and Technology developed the SHA-1 to fix the security issues found in its predecessor. However, weaknesses were still found in the SHA-1, which led to the creation of SHA-2 family in 2001. It is called a family because it consists of a total of 6 hash functions, each with different sizes or hash values, or in layman's terms, sizes which are indicated in their numbers. So SHA-224 is 224-bit long, SHA-256 is 256-bit long, and so on. SHA-512.224 and 512-256 are just truncated versions of the others. So, how is the SHA more secure compared to its predecessors? In order to answer that, I will first give a brief overview of how the secure hash algorithm works. In this presentation, I will focus on SHA-256 primarily because it's the most widely used type in authentication protocols and is actually the one employed by Bitcoin. So, how does the secure hash algorithm work? SHA takes an input of variable length and always converts that into an output of fixed length. The message size or the size limit of the input and the message digest size or the length of the output, aka the hash value, both depends on the type of SHA. In the case of SHA-256, it can take an input of any length between 0 and 2 to the power 64 and will always generate a hash value that is 256 bit long. A single character, a word, a sentence, a paragraph, or even an entire book as an input will have the same length of hash, which is 256 bit long. It converts data into an alphanumeric hash in hexadecimal representation, meaning its hash value is composed of a total of 64 characters that are either letters or numbers. You may be wondering, 1 byte is equal to 8 bits and 1 character in hex can be represented using a total of 4 bits. Since the hash value is 256 bit long, 256 divided by 4 bits per character results to a total of 64 characters. Secure hash algorithm is considered as a secure cryptographic hash because of its following properties. Number 1, it is deterministic, meaning it will always produce the same hash or the same set of 64 alphanumeric characters for the same input. This is important because if the result differed every time, then we will have no way of keeping track of the input data that we hashed. Number 2, it is quick to compute. SH is not a form of encryption, it is designed to be more of an authentication method and not as an encryption that must be decoded, which leads to the third property, which is pre-image resistance. Pre-image resistance means that it is infeasible to determine the original input data from the output hash. Infeasible because determining the input is not entirely impossible, since the hash generated for a particular input will always be the same. However, since the only way to determine the input is by brute force or trying every possible combination of the input data, then this threat becomes insignificant. The fourth property is the avalanche effect. This means that a slight change, even just changing a character from lowercase to uppercase and vice versa, will completely change the resulting hash. This property makes the hash pre-image resistant. Finally, the fifth property is its resistance to collision. Collision is when two unique inputs have the same hash value. As I mentioned earlier, the size limit of the input value for the shadow for the SHA-256 function is 2 to the power 64, which is infinitely large. This means that almost anything can be hashed using SHA-256, and all of these things, regardless of their size, will always be converted to a 256-bit string. So, how is it possible for every output to be unique? That answer is no, hash function is completely collision free. However, like the pre-image resistance property, it is highly unlikely to find two input values that will yield the same hash value. It will simply take too long, which makes it an insignificant threat. So, how is SHA-2 more secure compared to its predecessor? This is because SHA-0 and SHA-1 both produce only 160-bit long hashes having a shorter length. The hash values that they produce have lower number of different combinations, which makes them more susceptible to collision. So now we dive into the mathematics behind the hashing algorithm of 256. This has been divided into 6 parts in the presentation. For the first part, let's discuss some of the terminologies that we will encounter. Number 1, bit. Bit is a binary digit having a value of either 0 or 1. Byte. Byte is a group of 8 bits. Number 3, a word is a group of 32 bits or 4 bytes, since 32 divided by 8 is equal to 4. Number 4, hexadecimal notation is a number system of base 16. Finally, a hex digit is a representation of a 4-bit string So now we will take note of the operations that are used for SHA-256 algorithm. So for our first operation, we have the exclusive or logical operation which lists a value of 1 if true. The operand have different values and false or 0. Otherwise, the OR operation is to give a balanced representation of its different operands. The second operation is the right shift operation. It is denoted by the symbol. This simply shifts the bits of the 32-bit word to n number of positions to the right. So for our first example, the n is 1. So we just have to move every digit to the right, giving us 0, 1, 0, 1. In the next example, our n is 3. So we just move each of the digits the right for a total number of 3 times, giving us 0, 0, 0, 1. The third operation is the rotation right, which also moves the digits of the 2-bit word by n number of positions to the right. So, how is it different from the previous operation? Here we move the bits to the right. The one in the end is stored back at the leftmost digit of the word instead of disappearing completely, which is why it is also known as the circular right shift operation. The fourth and the last operation is the addition modulo 2 raised to the power 32. This is done by first adding the integer equivalent of the binary words together, then getting the remainder when this sum is divided by 2 raised to the power 32. We just simply convert the remainder which is integer to a binary word. This operation can be done directly using the binary words by following the rules of the operations in terms of the binary system. So here is an example of this operation. Now we shall discuss the functions used by SHA-256. First is the lowercase sigma 0 function, which takes 132-bit word, performs a rotate right on that word for 7 and 18 number of positions, and the shift right operation for 3 positions, and then XORs each of the results together. The next 3 functions all operate the same as the first one, except that the number of positions of every operation in each function is different. For lowercase sigma, it takes a single 32-bit word, rotates right by 17 and 19 positions, and shifts right by 10, and then XORs the results together. For uppercase sigma 0, it also takes a 32-bit word and also rotates right but for 2, 13 and 22 number of positions each, and then XORs each of the results together. For uppercase sigma 1, on the other hand, it also takes a 32-bit word and also performs the rotate right operation but for 6, 11 and 25 number of positions each, and then XORs the results together. The only difference between the lowercase and uppercase sigma functions is that the lowercase sigma function uses the shift right operation while the uppercase sigma function does not. There are two other SHA-256, but unlike the previous functions, these ones do not make use of the rotate right and shift operations. One is the choice function denoted by SHA, which takes 332-bit word and is defined by in terms of a logical statement as ending x and y and not x and z respectively, and then performing the XOR on these 2 bits. However, there is a simpler way of interpreting this function. Every bit in the result depends on the value of the bit at that particular place. If the bit in x has a value of 1, the resulting bit will be whatever value is in y. Else, if the value in x is 0, the result would take the value of z at that place. The last function is called the majority function denoted by MAJ. It also takes 332-bit word inputs as a logical statement. It is performed by ending x and y, x and z, and y and z separately, and then performing the extra operations on these 3 results. However, there is also an easier way to interpret this function from the name itself. It simply does it takes the bit that appears most frequent among the 3 bits in every place of the 3 inputs. Now, we will discuss the constants that are used in the SHA-256 algorithm. SHA-256 is using a sequence of 64 constant 32-bit words denoted by k sub 0 to k sub 63. So where do the values come from all of the constants? We take the first 32 bits of the fractional parts of the cube roots of the first 64 prime numbers. The fractional parts of the cube roots of prime numbers give random looking bits, which makes them a good source for a constant that can mix up the message being hashed. So now we dive into the actual hashing algorithm of the SHA-256. This will be discussed in two parts. The first part is the pre-processing, or the processes that we must first do with our input before the computation begins. In pre-processing, there are four steps. The first thing we have to do is convert our message into binary. So how? There is what we call the American Standard Code for Information Interchange, or simply the S2 code, which assigns one particular value for every function character. So using this, we just simply get the number assigned to each character in the message and correspondingly into binary. So for example, we have the input A, B, C. Based on the ASCII table, A is equal to 97, B is 98, and C is 99. Converting these numbers to binary, we have the following bit string. In binary, we are now at the second step, which is expanding. Now we are at the second step, which is expanding the number of bits in a message to the nearest multiple of 512. Since the SHA-256 hashes data in chunks of 512 bits, how are we going to increase the number of bits to 512? It is simple. We will just add zeros to the message, but before we do that, we will first have to append a 1 at the end of the message to serve as a separator between the actual message and the trailing zeros that are just padded for expansion. After appending a 1 at the end, we will have to start padding the message with zeros. Exactly how many zeros are we supposed to add? Let's look at the formula where L is the length of the message or the total number of bits of the message, and K is the number of K bits, 0 bits that will pad. So 1 plus K is congruent to 448 modulo 512. It might seem intimidating. It only means is that we'll have to add K number of zeros such that the total number of bits of the message plus 1 bit because of the separator we added earlier plus the number of zeros that we will add will have a remainder of 448 and divided by 512. So counting the total number of bits of our actual message ABC, its length is 24 bits, then we convert the number 24, which is again the length of the actual message, into its binary equivalent, which gives us 1100. If the resulting length is less than 64 bits long, we simply have to add 0 starting from the left of it to make it 64 bits long, and then just append this to our 448 string previously, and there we have a 512 bit string which we call a message block. We can take more than one message block, each containing 512 bits each. This is possible when we have an actual message that is already more than 512 bits long. In that case, we will have to pad zeros until its number of digits reaches the next nearest multiple of 512, such as 1024 and so on. But in our case, since our input ABC is just short, we will only have one message block. Nonetheless, the operations done on each message block is just the same. Hence, what we will be doing next for our one message block, we'll just have to repeat it for the other blocks if any. Okay, so now 48 more words, and to prove that we will be using the following 16 words and the formula shown below. You just have to apply what we learned earlier in order to get the next term. For example, lowercase sigma 1 here is just a function that we discussed previously which does 3 operations to a word, namely rotate right by 7, rotate right by 18, and shift right by 3, and finally exhausts these 3 resulting values together. The t minus 2 here means that the input for the lowercase sigma 1 function is at the term that is 2 units before the current term being computed. So, for better understanding, we have an example. For example, getting the 17th word, we have t equals 16. Since we started at index 0, to get its value, we simply have to do the lowercase sigma 1 function to the term at 7 minus 2, which is t equals 15, or simply the term ahead of it by 2 places. And we simply take the value at t minus 7, which is at t equals 10 in this case. We don't have to perform any function for this as stated in the formula. Next, we get the term 15 places before the term being generated, and perform the lowercase sigma 0 function on the value. The lowercase sigma 0 function takes an input, performs rotate right by 17, rotate right by 19, and shift right by 10, and then XORs the results together. Then we simply get the value 16 places before the 17th word, which is at 16 minus 16 or t equals 0. Finally, after getting the 4 values, we just perform the addition modulo 2 raised to the power 32 operation that we discussed earlier, which is adding the values together and taking modulo 2 raised to the power 32 to constant the number of base to 32 bits. This formula will be used for every succeeding words at t equals 17, 18, 19 and so on until we reach t equals 63, which means we already have 64 words in the message schedule. Now that we have prepared our message schedule, we are finally at the last step of the preprocessing, which is setting the initial hash values. We have to initialize a total of 8 hash values. The values of each is taken from the first 32 bits of the fractional parts of the square roots of the first 8 prime numbers in binary notation. I know it is overwhelmed by all of the information, but because we're finally at the second and last part of the hashing algorithm, this part has 4 steps, but we already did the first one earlier, which is the preparation of the message schedule. So now we will head on to step number 2. 2 is initializing what we call the 8 breaking variables, which are the 8 slots where the words will fall into later on. These are signified by letters A to H and initialized using the 8 initial hash values as shown earlier. Step 3. We will now be doing the compression functions where we are going to modify the values stored in each working variable using the values in our message schedule, which is denoted by W sub T. Note that the process I am giving versus is shown will be done to all 64 words, hence the T equals to 0. T equals 0 to 63. Hence in this process we will be needing two temporary words T sub 1 and T sub 2, each with the corresponding formula that will be using the words constants and working variables as input. Let's start with T sub 1. T sub 1, the formula simply means that we have to take the working variable h and the upper case sigma of e of the working variables e, f and g. We also need to take one word in the message scale denoted by w sub t and its corresponding constant k sub d, and the words we simply have to add all the 5 values together, and we have to take the sum modulo 2 to the 32 also. We also perform the modulus function after getting the sum to contain the number of digits to 32 bits. To illustrate, let's look at this. Since we're just starting, we get the first W0 and the first constant K sub 0. Next, we get the choice of E, F, and G and 25. Then square them together. Then we get H, and finally add these three values with W sub 0 and K sub 0. We now head on to T sub 0, which is simpler for the first value in the equation. We just have to perform the uppercase sigma 0 on a then on A, then we just perform the majority operation on the working variables A, B and C to get the second value. Finally, we perform the addition modulo 2 raised to the power 32 operation on the two values, and there we have our second temporary word. So again, we must take the first majority of A, B and C. Then we perform the uppercase sigma 0 function by rotating right to 13 and 22. Then XOR them. Finally, we just add the two values together. After obtaining the two temporary words, we now update our working variables. The first thing we should do is move all of the values of our working variables by 1. So we store the value of a working variable to the next variable and lose the last one since there is no variable after it. And then we put a new word into A, which is the sum of T sub 1 and T sub 2, or the value obtained when we add the values in the T sub 1 and T sub 2 and take modulo 2 to the power 32 of the value afterward. We also have to add T sub 1 into E. So this is the process repeats until we have done it for every single word and constant. Remember that we have 64 words in our message schedule with corresponding 64 constants. Hence we have to perform the compression of each of these words for a total of 64 times. So in step 3.4, we have to repeat and we have done for every word constant. Remember, we have 64 words in message schedule with corresponding 64 constants in step to perform the compression on each of these words for a total of 64 times. Now, coming to step number 4, we have to take the initial hash values that we started with and add the end result of a compression to each hash value, and then we are done with the compression of our first message block. We did this first. Now, we will have to do step 5, which is performing the set process for each block, each using the intermediate hash values generated in the previous blocks. This will be done until every message block is compressed into our hash values. Finally, we are now at the final step of the algorithm. Once all of the blocks are compressed, the final hash values are each converted into their hexadecimal representation and finally concatenated together to form the final message digest that is 256 bits long or 64 characters long in hexadecimal representation. We have 8 hash values times 32 bits is equal to 256 bits, which confirms that the final message digest has a total of 256 bits. And there we have finally converted our input ABC into a hash value using SHA-256. SHA-256 is commonly used in validating software that are downloaded from websites. It is also used in logging onto various operating systems such as Unix, and is also applied by companies when storing their users' passwords. When a user enters a password, the password usually runs through a hash algorithm, and the output hash value is compared to the company's user database. SH256 is also used in preventing software piracy and detecting unauthorized file modification such as web page defacement, signing database key system file modification, virus signature update, and so on. With its vital role in authentication and security, a lot of us may have thought that SH256 is a highly complex algorithm, but it is actually very easy and if we study the algorithm after dissecting. Thank you for listening to my presentation. If you have any questions, you can ask.